This lesson is 8.6, Changes in Scale. What will we learn today? To find the surface area and volume of similar solids.
Monuments. There are all kinds of man-made monuments around the world, and they all come in various shapes and sizes. You can find a lot of them in Washington, D.C. The Lincoln Memorial and the Washington Monument are two of my favorites. I just bought a souvenir of the Washington Monument at the gift shop. The miniature is about 6.5 inches tall. It is 1/1000th of the real monument, which is much, much bigger. In fact, at 555 feet 5 inches, the Washington Monument is the largest stone tower in the world. Compare that to the height of the Lincoln Memorial. The Lincoln Memorial is 99 feet tall. Using the same scale as my miniature Washington Monument, a souvenir of the Lincoln Memorial would only be a little over 1 inch. Could we figure out how the volumes of the souvenirs and the real monuments are related? In this lesson, learn the relationship between scale factor, volume, and surface area of similar solids.
We have two key concepts today. The first one is surface area of similar solids. So in words, a scale factor is how much larger or smaller one solid is than another. Similar solids have the same shape and their corresponding linear measures are proportional. So if we have two similar figures similar solids A and B, the surface area of B is going to be the surface area of A times whatever the scale factor is squared. So let's say they're saying it's 2 times bigger than surface area A, then we would take surface area A times 2 squared. If they're saying it's 4 times bigger, then it would be 4 squared. Example 1. The surface area of a rectangular prism is 78 square centimeters. What is the surface area of a similar prism that is 3 times as large? So we're going to use the surface area formula, 78 times, and we're looking at the scale of 3 times as large, and we're going to square that. So 3 squared. So we have the 78 comes from the surface area of, I guess you can say prism A, and prism B is going to be 3 times as large. So that's where we get the 3 squared. Okay. 3 squared we all know is 9, so we're going to take 78 times 9, and that gives us 702 square centimeters. Our second key concept is volume of similar solids. Very similar to the surface area of similar solids. In this case, we're taking the volume of B is equal to the volume of A times whatever the scale factor is cubed. So if the scale factor is 1/3, then it's going to be 1/3 cubed. If the scale factor is 6, then it's going to be 6 cubed. Example number 2. A triangular prism has a volume of 432 cubic yards. If the prism is reduced means it's going to get smaller, to 1/3 of its original size, what is the volume of the new prism? So we're going to take the volume, 432 of figure A, or prism A, times the scale. Again, we're reducing by 1/3, which is 1/3, and it's cubed. We're going to take that 1/3 cubed. So 1/3 cubed is 1/27th. Multiplying that times 432, which will give us 16 cubic yards. Remember, we're using yards. Cubic yards is our unit of measure. So the volume of the new prism is 16 cubic yards. This is a real-world problem. The measurements for a standard hockey puck are shown at the right. A giant hockey puck is 40 times the size of a standard puck. Find the volume and surface area of the giant puck. Use 3.14 or 3 1400ths for pi. So you can see that we have our height is 1 inch, and our radius is 1.5 inches. So find the volume and the surface area of the standard puck first. So the volume, it's in the shape of a cylinder, so it's pi times radius squared times height. So again, we're using 3.14 for pi. Our radius, 1.5 squared times 1, will give us a volume of 7.065 or 7 65 thousandths cubic inches. Remember, volume is cubic. Our surface area is going to be 2 times pi r squared plus 2 times pi times radius times height. Excuse me, those are formulas that we've been using in our previous lessons. So now we're going to substitute. In the first part, we're going to substitute 3.14 for pi and 1.5 for the radius squared plus 2 times the times 3.14, sorry, times 1.5 times 1, all substitution in this area here. Once we simplify, we get 14.13 or 14 1300ths for the first part. And the second part is going to be 9 4200ths. Total square surface area is 23 55 square inches. Let me say that again, 23 5500 square inches. So that's the volume and surface area of the standard puck first. Now we're going to find the volume and surface area of the giant puck using the computations for the standard puck and the scale factor. So now we know the volume. And then we're going to take, so volume times 40 cubed. The 40 comes from the sentence, a giant hockey puck is 40 times the size of the standard puck. So 40 cubed. We know that the volume was 7.065. That's where we get this from. 40 cubed, use your calculator obviously, we get a volume of 452,160 cubic inches. Now for the surface area, we take the surface area, which we know is 23.55, which we got from step 2, times 40, this time it's squared. Once again, using our calculator to simplify this step, we get a surface area of 37,680 square inches. So to finalize, the giant hockey puck has a volume of about 452,160 cubic inches and a surface area of about 37,680 square inches.